problem in a little bit after we talk about what these Lagrange multipliers are. So you can wait to copy this down until we actually get to it, but I just wanted to give some context of where we're going with this method. So we're still using maxima and minima, just like we were in section 3 that we did on Tuesday. But there is another layer to the situation in this kind of problem. So this example, suppose a manufacturing firm has budgeted $90,000 per month for labor and materials. If X thousand dollars is spent on labor and Y $1,000 is spent on materials, the monthly output is this of whatever they're manufacturing. Then how should the $90,000 be allocated to labor and materials in order to maximize N? And what is the maximum of N? So this is different from our other maximum and minimum problems because on our other problems, we've just been taking like a profit equation and finding the maximum profit we could make, or the maximum revenue, or the minimum cost, or whatever. And so we might end up having a maximum profit that's not actually reasonable to do for that specific company because we were never taking into account a possible budget. So in this context, we have what we'll call a constraint. So in this case, we want to find the maximum output possible within the budget that we have. So instead of just saying we can spend as much as we want, as long as we can get a maximum profit or whatever it is, now we are putting some limits onto what our variables can be. So we will come back to this example in a little bit, but I'm going to bring up what that method actually is and what Lagrange multipliers are. So this, like we did on Tuesday, I have the steps here, and so I'm going to copy and paste these steps as we do the problem, so each of them is ready to go for each of our steps. So you don't necessarily have to write all of this down now. You can wait until we get to the problem. But we're going to have 4 steps. And so in each of our problems, we're going to have something that we want to maximize or minimize, and that will be a multivariable function. So it will be a z equals f of xy type of thing. But we will also have something that a constraint. So it's going to be subject to some other function, and we'll see that in a little bit. So this is our constraint, which in our situation is going to be a budget. So that's going to put a limitation on our function that we're trying to maximize or minimize. The rest of these we will get to as we're doing the problem because it will be easier to understand what we're doing with an example. But there is a little character in here that you may or may not have seen before, and that is lambda. Lambda is a Greek letter. Like a lot of characters we see in math. And that is the Lagrange multiplier. So that's where this method gets its name. So we're going to take these steps into a problem, but first I just want to note a couple of things. We're going to be making a new function which will have 3 variables. So we've been doing functions with x and y, and this lambda, the Lagrange multiplier, is going to become a 3rd variable. So we're adding 1 layer to what we were doing on Tuesday, but we'll be doing a similar kind of thing where we're finding the critical points, which involves partial derivatives. And we have this 3rd little variable, lambda. So I just want to emphasize that lambda is not different from x and y in any way. It looks a little weird if you're not used to seeing lambda, but it's just like a regular variable that we use. So let's actually look at a problem. So I'm going to start to copy and paste these steps. So here is our problem. We want to maximize f of xy equals 25 minus x squared minus y squared, subject to this constraint that x plus y equals 4. So this is not a word problem. We don't have a real world situation here, but this is just a practice before we get to that kind of problem. So our first step is to write the problem in the form so we're trying to maximize. And so this just means like write down, identify the function that we're trying to maximize. So in this case, it's f of xy equals 25 minus x squared minus y squared. And our constraint, the thing that our maximizing is going to be subject to, we need to write in this form, g of xy equals 0. So in a minute, I'm going to put up a poll to identify what g is. So our constraint is x plus y equals 4. But we need it in this form, g of xy equals 0. So basically, we're trying to identify the function g of xy. Based on our constraint x plus y equals 4. So the question that I am going to put up in the poll is, what is g of xy for this problem? So I'm going to put up a poll. So there are 4 choices. And so I want you to think about what our constraint is, the x plus y equals 4, and the format g of xy equals 0. Okay, looking good so far. So another 15 seconds or so. Okay, I am closing the poll. Okay, so this looks pretty good. There are only 2 choices chosen, which is good. So we're not all scattered around. So the key here is that our subject to needs to be equal to 0. So that's the step 1 here, is to make sure that we have a function equaling 0 based on our subject to equation that we're given. Which means, I'm just going to erase all of this for now and rewrite it. If we have x plus y equals 4, all we need to do is get that to be 0 on one side. So x plus y minus 4 equals 0. So the key here to this subject to part is to get 0 on one side. And the thing that's on the other side is our g of x. xy, excuse me. So that's the key step here. Maybe sometimes it'll already be set to 0 in the original problem, but if not, we just need to get everything onto one side. And this will always be a fairly simple little equation, so it'll just be a matter of subtracting stuff over to the other side. Okay, so that is step 1. So these 2 functions that we have, our f, which is the thing we're maximizing, and it could be called something else if in the particular problem. And we have our g, which is going to constrain our function. Okay, so here is where we get to build our 3-variable function. So I'm going to go up and grab step 2. I should have also said these steps are in the book on page 453 as well. I'm going to write that here real quick. Okay, so we're going to form a new function called capital F. And that capital F function looks like this. So we have capital F of, and now it has 3 variables, x, y, and lambda. And that's formed by adding little f of xy plus lambda times g of xy. So here we have capital xy lambda. So we have our little f, which is the whatever function we're maximizing. So that's our 25 minus x squared minus y squared. And then we're adding lambda times the g of xy that we found in step 1. So this is step 2, is just putting this new 3 variable function together. So we have x, y, and lambda in this function. It's not necessary to distribute that lambda, but it'll probably help in the next step. So I'm going to go ahead and do that. So we're going to have lambda x plus lambda y minus 4 lambda.
Why do you put one on the front, one on the back?
No particular reason, mostly because it's just, it would be kind of weird to write lambda 4, just because normally when we have a
Variable.
A number in a variable, we put the number first.
Okay.
Yeah, and I just feel like it looks better with the lambda before the x and the y. So that is not any math reason, it's just a sort of style reason. So
is lambda,
sorry, go ahead.
Or is it a constant?
So it is going to be a constant for this problem. It's technically a variable right now because we have this function that is in 3 variables, x, y, lambda. But the point of this is to solve it to find lambda, which will be fixed. So it is a variable in this context, since it's one of the variables in this 3 variable function. But there's going to be one specific lambda that gives us our maximum potential here.
And what does the Lagrange multiplier represent?
So once we finish this example, I want to look at these on a graph to see what's going on here. The Lagrange multiplier is basically a vector, which is, this word came up last class as well, which some of you have probably worked with and some maybe have not, because it's not a prerequisite for this class. But it's basically a way to figure out where our function can be at its biggest still keeping with this constraint that we have. So it's a scalar. That's the word we often use, that like is a constant that multiplies to something to make it bigger or smaller to move it around. So it's basically the number that's scaling our maximum function to the constraint to make sure that our function is as big as it can be without going out of bounds from the possible constraint.
So is it kind of like a tangent line?
Yes, we are actually looking for a tangent. These last 2 sections are a little uncomfortable because they rely on a lot of heavy math that's just not a part of like this class. And so there's a lot of like hand wavy kind of stuff that's like, this is just a thing that we have to use. But yeah, we are basically looking for where this function that we are maximizing becomes tangent to the constraint. And the Lagrange multiplier is the thing that lets us find that. So we have this 3 variable function now. And this is now what we are maximizing. So even though our actual goal, come on, our actual goal is to maximize our original function in just x and y, we're going to be optimizing actually this capital F function. But to do that, we will find the critical point of capital F in the same way that we found critical points on Tuesday in section 7.3. We just have one more variable here. I did not copy that whole thing. Didn't sleep very well last night, so I just feel like I am like not fully functional today. So sorry for my slowness. There we go. Okay, so step 3. We are finding the critical points of capital F now, so our 3 variable function, which means we need to find the partial derivative of F with respect to X, with respect to Y, and with respect to lambda. So remember on Tuesday when we were optimizing functions in 2 variables, we had to find the critical points by finding the partial derivatives and setting those to 0 and solving. We're doing the same thing here. We just have a third partial derivative since we have a third variable.
So x will be a negative 2x plus the little a thing. What's it called? A tanda?
Lambda.
Lambda.
Yes. So to negative 2x, yes, plus lambda. Exactly. So doing the partial derivative with respect to x, so we're just looking at the terms with an x in them, and that would be negative 2x plus lambda. So then we would go on to y. And we really have the same thing.
Negative 2y plus lambda.
Right, exactly. Negative 2y plus lambda. So lastly, we need our partial derivative with respect to lambda.
I assume it'll be x plus y minus 4.
Exactly. So we would be looking at each of these terms with a lambda in them. And since lambda is just 1 for each of those, we're essentially taking the coefficient of lambda from each of those.
Now, if there was a square root on top of like the x, would it just be x squared?
Square on which x?
Like the lambda x?
Something like this?
Or square root, yeah. So then it would just be square root of x?
Yes, exactly.
Okay. Will there ever be like a square root or a power or something on the lambda?
No, not on the lambda. And that's because of how we form this function, the capital F. It's always our function we're starting with plus lambda times whatever g is. So lambda is not in either of those original 2 functions. The only place it comes in is to multiply with g. So lambda will never have any powers on it or anything. It'll just be itself.
Okay, thank you.
Mm-hmm. And so just to note, we could have found all of these partial derivatives from the version of capital F where lambda wasn't distributed. And sometimes people think that that is easier. I like to distribute it because I think when we're first getting used to partial derivatives, it's easier to look at it term by term. But if you can do it without distributing, that's fine too. So either of those capital F's is fine. So most of the work for these problems is algebra. So I mentioned on Tuesday that when we were doing the solving the system, that there aren't really going to be many systems in 7.3 problems. But in 7.4 problems, we always have a system. So that's why I wanted to do a little warm up of solving systems on Tuesday so we could refresh before getting here. So on Tuesday, we did an elimination technique. My brain today. Here, I generally think that these are easier to use substitution, but it's still kind of up to you and what you think is easiest. So we'll notice that in our first two equations for this problem, we have just the variable that we were doing the partial derivative with respect to and the lambda. So we have x and lambda in our first equation, y and lambda in our second equation. And then this third equation, we have x and y. So in this situation, I personally think it's easiest to solve each of these first equations for lambda. No, solve them for x and y so that we can plug them into this formula or this equation. So if we can solve, oh, sorry, go ahead.
So x and y equal 2.
Right, exactly. So if we know what x is in terms of lambda and what y is in terms of lambda, then this equation can be all lambdas because we can replace x and y with stuff in lambda. So this first equation is just here. So if we solve this equation for x, we would just subtract lambda over to the other side and then divide by -2. So we'll end up with x equals lambda over 2. And if we solve this other one for y, we have -y plus lambda equals 0. That is exactly the same, but in y, so we will end up with y equals lambda over 2.
Is there an actual value to lambda?
There will be.
Okay.
We will find it. Right now, we don't know. It's not like a pi where it's a fixed value all the time. It's a variable, so we don't know what it is yet, but we will find it.
Okay.
So now we can take this x and y and plug it into that third equation. So our third equation was x plus y minus 4 equals 0. But we know x is lambda over 2. Y is also lambda over 2. So now we have an equation in all lambda, and we can actually find out what it is. And so solving this, if we have lambda over 2 plus lambda over 2, that's 2 lambda over 2, which is really just lambda. And adding 4 over to the other side, we get lambda equals 4.
How did you get the 2/2? Oh, because you have two lambdas. You added them. Gotcha. Okay.
Yes, exactly. So the weird thing here is that we're making this big deal about the Lagrange multipliers and the lambdas, but the lambda is actually not the thing that we really care about in the end. We need it in order to do this solving. But what we're actually looking for is the x and the y, because those were in our actual original function. So we can plug lambda in. So x equals lambda over 2. And now we know that lambda is 4. So x is 2. And we know that y was lambda over 2. Lambda is 4. And so y is also 2. So when we solve the system, we end up with x equals 2, y equals 2, and lambda equals 4. So we get a value for all three of our variables in our 3-variable function. So let's look back at what we are going for here. Okay, so that was the end of step 3. So the critical points of f would be the solution to this system, which means whatever x, y, and lambda we get after solving those partial derivatives set to 0, which is what we just did. So now all we have left is step 4, which is really just the conclusion. So I'm going to copy and paste that so we can talk about it. So step 4 is saying that if this x naught, y naught, lambda naught, so these little knots or the sub-zeros are just referring to the specific values that we found in step 3. So these are the values from step 3. So if that's the only critical point from step 3, then x naught, y naught will produce the maximum or minimum of our original function. In parentheses, I have this little note, if there is more than one critical point, so if we had found more than one x, y, lambda in step 2, we would have to plug it in to find which was the maximum and which is the minimum. That's not actually going to happen in this class. We will always just get one x, y, lambda from step 3. So we don't actually need to worry about this. Unnecessary. It's just a note that that can happen, but it won't here. So what this is saying is, in step 3, we found x equals 2 and y equals 2. So the lambda doesn't
When
actually.
it says to plug it in, that's the.
Sorry, you are breaking up. I didn't actually hear any of that.
Can you hear me?
Yes.
My internet is. So when it says to plug it in, we're plugging that into the AC minus B squared if we needed to do that.
We don't need to do that actually, in this case. The
But that-
AC minus B squared only works for two variable functions, xy functions, and there is like an analog to that for more variables, which we don't do in this class. And so we don't actually need to do that. We know that this xy that we found in step 3 is a critical point of our 3 variable function. And if we're trying to maximize it, then we can assume that that definitely is where the maximum is going to happen. So our x naught y naught, which is just the x and y we found in step 3, are going to produce the maximum or minimum that we are looking for. So that means that the max of our original function, which was so long ago, 25 minus x squared minus y squared, so the maximum of this function, and I should have said subject to that constraint that we started with, is at 2, 2, which means that x equals 2 and y equals 2.
And that's it?
Well, we really should do one more step. I was just going to look back at our instructions to make sure. Oh, gosh. Yeah, so we do need to plug it in to find the actual maximum. I should have put that, so I'm going to add that to step 4.
You put plus.
Thank you.
You're welcome.
To find the max. So if this were a minimum problem, we would plug it in to find the minimum, but since this is a maximum problem, we are plugging it in to find the max. So we would plug these two into the original function. So we have f of 2, 2 equals 25 minus 2 squared minus 2 squared. So that will be 17.
So would that be like 17, 0 as our point? Or just 17?
Just 17.
Okay.
So this is saying when x is 2 and y is 2, the function is 17. So this would be like the z value.
Oh, okay.
So this is it. It's the algebra in this kind of problem is usually the most involved step. Step 3 is the part where most people get stuck if they get stuck, just because this system It's not going to be anything super crazy, but we do have to remember how to use substitution and solve systems of equations here. So I am going to bring back that other example, and I'm going to leave that up for just a minute. Oops, sorry. Okay, so I have prepared a graph that we're going to look at in just a second to sort of visualize what's happening here. But let's look back at this problem. So this is the same problem that we started with, giving some context to what we're doing here. So this manufacturing firm has budgeted $90,000 for labor and material. So this word budget is kind of the key word that's going to have to do with our constraint, because that's restricting how much we can spend. If X thousand is spent on labor and Y thousand is spent on material, and the monthly output is this, so that's the n of xy, a function of x and y, then how should the $90,000 be allocated to labor and materials? So let's go through those same steps to start off with, and then I want to show the graph of what we're doing. So step one, we are trying to maximize.
Is that n xy comparable to our lowercase f xy?
Yes,
Okay,
it is. So the lowercase f of xy, I'll go back for just a second. In the like general form, we use a little f since that's just kind of the default name of a function. But in a lot of application problems, there's some other name for it. So really the key here is that little f, whatever it is the function that we're trying to maximize or minimize. So when we are looking for maximizing n here, we're trying to maximize output based on this budget. That is the indication that this is the function that we're trying to maximize. So that is analogous to the little f in the steps.
okay, thank you. I just didn't know because it was a capital N, maybe it was supposed to be like a capital F replacing.
Yeah, that is confusing, and you can see where that comes from, but
Okay.
yeah, it's what we're trying to maximize or minimize that's the key that tells us that. So we'll always be given that function that we're trying to find the maximum of. Or minimum. I can't remember if there's a minimum on your homework, but it'll all work exactly the same way. And then we also need our subject too. So this is the one we might have to think about a little bit.
X plus y minus 90,000.
Almost. the important thing here is to note that X and Y are in thousands. So for example, if X were 2, that would mean we're spending $2,000 on labor. So X plus Y is not going to be 90,000.
Would it be 9 million?
Oh, other way.
Oh, 9,000. 9?
90.
90.
Some number of zeros after 9. Yeah, so X and Y are in thousands, so X plus Y should equal 90. Since X and Y are in both thousands. So for example, if X was 5 and Y is, no, if X was 50 and Y was 40, that means we're spending 50,000 on labor and 40,000 on materials. So together those would make the $90,000 budget.
Gotcha. Okay.
So I usually like to write the subject to or the budget equation not necessarily equal to 0 first, just because I think when we're thinking about a budget, it's helpful to think if we take our labors and materials and add those together, we should have our full budget, the 90,000. But we do need it to actually equal 0. So if we start by writing it not equal to 0, we need to rewrite it equal to 0. So that's our budget. So before we go further, I'm going to bring up a graph of these two functions. Oh, and actually, I just realized I can do something better than what I just did. Okay, so the top equation here is our budget equation, the X plus Y equals 90. The bottom equation, I just solved our N function for Y. For some reason, I don't know if that was actually necessary, but it felt better to write Y equals here. So this, what's written in this blue line is just this budget equation solved for Y. So we have N, and then I added the 6x over, so N plus 6x, and then divided by 3x to get Y by itself. So now it's a Y equals. But N is the output, and so now I've added a slider N and didn't make the slider big enough, so let me change that. If that works. So this blue curve is the relationship between X and Y. So X and Y are our regular two axes. Depending, the relationship between X and Y and the different outputs. So if we're only outputting 100 units of whatever we're producing, our curve is going to be way down here. And so this represents all of the possible allocations of our labor and materials. So here labor is on the x-axis and materials are on the y-axis. So if we spend $19,600 on labor and $3,700 on materials, we can make 100 units of our thing. But why would we only want to make 100 units if that's not even close to meeting our budget? So our budget is up here. So any point on this red line would fit the budget. That's all of the points that fit, that fit labor and materials equaling 90,000.
So is anything less than the the x plus y equals 90? Anything less than that, is that a deficit?
No, anything less than that would be that we're not using the whole budget.
Okay, so it's just based on budget. Okay.
Yes. So like here, this point, I can't get on any exact points here, but here would be spending 20,000 on labor and 30,000-ish on materials. So that would only be about $50,000 and our budget is 90,000. So the goal of the Lagrange multipliers is to find this sweet spot where we're producing as much as possible while using our whole budget. So we don't want to be under the budget curve because then we're not spending as much as we could be. So we're not producing as much, but we also can't go above. So like if we have a production of 10,000, now the curve is way out here and that's way out of our budget. Any XY pair out here is going to be too much. So here is spending 55,000 on labor and 62,000 on materials. So that's way out of our budget because that's going to be over, well over $90,000. So depending on N, we are trying to find that sweet spot where the output function and the budget function actually meet. And I don't think I'm quite getting it there. We'll find out what it is in a little bit. But we're trying to find a point where they just meet. So we're still within our budget, but we still have the maximum output possible. So this method of Lagrange multipliers is doing this in a weird way. It's finding the best place where those two functions are tangent. So let's go on to our next step. And step 2 was to form that free variable function. Which is f of xy lambda equals, so our actual step in the like official steps uses the little f as just the general function that we're trying to maximize. But that in this case is n of xy. So it's always that function we're trying to maximize or minimize that goes first. Then we have our plus lambda times, oh, I'm getting ahead of myself, times our budget or our constraint. So we did find that before.
And you're always adding those two together, correct?
Yes.
Okay.
Always adding. So n of xy was 3 xy minus 6x plus lambda times x plus y minus 90.
So then factor lambda in.
Yes. So now we have this xy lambda function. And so our step 3 so we want to find the critical point of capital F of x, y, lambda. And that is always found by finding the partial derivatives of each variable and setting them to 0.
It'll be 3y minus 6
3y minus
plus
6.
plus lambda.
Yes, exactly.
And then 3x plus lambda.
Mhm.
And then x plus y minus 90.
Yes. Just a little side note, now that we're seeing our second example of this, we'll notice that that partial derivative with respect to lambda is always just our constraint function. So here our constraint was x plus y minus 90 equals 0. So since that x plus y minus 90 is the thing multiplying to lambda, when we're doing a partial derivative with respect to lambda, that acts as its coefficient. So that whole thing will always end up being the partial derivative with respect to lambda. Just a little note, you can forget that and just do the partial derivative, but you should get that g every time.
Will these problems always, in the word problems, will they always be to the 1,000, the x and the y?
No, not necessarily.
Okay, so sometimes they'll be like 100 or 10,000.
Yeah, so like the first one we did, this was not a word problem. So those were just regular, whatever they came out to be. But it could be in, I don't think there are any that are 100 or million or anything like that. I think there are mostly 1,000, but we should
Okay.
definitely check every time.
Okay. Now I set them all to 0, right?
Yes, exactly. Set them all to 0. So again, if you solve these in a different way, as long as you're following all of the rules of solving systems, then there's generally more than one way to go about it. I like the way we did last time of solving the first two for x and y and then plugging them back in. So in this case, we have y in the first equation instead of x, but we can still do the same thing. Solve for y. So we would add 6 and subtract lambda to the other side. And then divide everything by 3.
Now, if we subtracted 6 and divided by 3 and then took over the lambda, would that make our answer wrong?
It wouldn't be wrong as long as you're super careful. So let me just look at that so we can see what we need to do there. So you said add 6, divide by 3, and then move the lambda?
Yeah.
So if we did 3y plus lambda equals 6, so we move the 6 over. Then we can divide by 3, but we have to make sure that we divide the whole side by 3, which can either mean the whole side or just each little bit.
Okay.
And that's fine. We would get y plus lambda over 3 equals 2. And then we would just need to move that whole lambda over 3 over. Which is what we would have gotten either way. It's just, I think that that way makes it more likely for people to
Yes,
forget
yes.
to divide by 3 on that lambda.
I would have.
Yeah. So I wouldn't recommend that way, but if everything goes right, then it's totally fine. And then we can solve the other one for x. This one is less involved, so we'll just move that lambda over. Then we get negative lambda over 3. So our third equation, the partial with respect to lambda, was x plus y minus 90 equals 0. There we go. And so we can substitute in what we just found for x and y. So x was negative lambda over 3. Y was 2 minus lambda over 3 minus 90. At this point, I want to remind you of an algebra technique that might help in some of these problems. This one would not be too bad to put those lambdas together since they have the same denominator. But when we have a problem with a fraction, and I just realized we can add together that 2 and the negative 90, so let's do that first. When we have a problem with a lot of fractions, especially if you're a person who doesn't like fractions, it's nice to get rid of them, which we can do by multiplying the whole equation by the least common denominator. In this case, it's just 3 and 3. If we had like 3 and 9 or something like that, we would multiply by 9. So we're multiplying by whatever the least common denominator is. And we have to multiply on both sides. The other side is just 0, but we should still multiply by it for good practice. So when we do that, we end up with 3 multiplying to each of these terms. 240, 260.
264. Yeah.
And all of those denominators now cancel. So we're left with negative lambda minus lambda minus 264. Oops. So you don't have to do that. We could have added those two lambda over 3s, negative lambda over 3s together to combine like terms. But sometimes these problems when we're substituting can get a little messy with fractions. And so it's nice to have this technique in your back pocket ready to go to just like get rid of all of the fractions. We just have to make sure that if we're multiplying by 3, every single term gets multiplied by 3. Cancels the denominators, is great. And then we have that 264 left. So negative 2 lambda equals 264.
So lambda equals 132.
That should
Oh,
be
a negative.
negative, yeah. That's right, yes. So like I said on the last one, usually this step of just solving the system is the most work, and it's not even calculus, it's algebra. But these are things that are easy to forget when you're not practicing them all the time. So that is step 3, or no, was that step? Yeah, that's step 3 of solving this system, setting all the partial derivatives to 0 and solving. So now we just found that critical point. Oh wait, no, we haven't finished finding the critical point, sorry. We got lambda, but we don't know what x and y are. So once we know lambda, we can go back to these two equations that we had in terms of lambda for y and x and find x and y based on our lambda. So I'm going to write those down here. So we have x was equal to negative lambda over 3. And y was, you already forgot, 2 minus lambda over 3. So now we can find x and y. Oops. And I just made a classic mistake that's really easy to make. I put the negative, but we have a negative in front of the lambda and a negative in front of the 132. So that should be a negative negative. So that's 64.
That's 44.
Thank you. Oh, this was 44, yeah, sorry. $44. And now we have 2 plus 44. Oh my gosh, 46. So the x and the y were the things that we were actually interested in. The lambda is the tool to get us to this x and y, but the x and y are the things that we're really looking for. So our question was, how much money should be allocated to labor and how much should be allocated to materials in order to get the maximum output based on our budget?
44,000 and 46,000.
Exactly. So 44,000. So we know that x is labor and y is materials from the original problem. So since x is 44 and we know x is in thousands of dollars, we are spending 44,000 on labor and 46,000 on materials. That doesn't quite answer the whole question, I don't think. Let's make sure. So, so we want to know, what is the maximum of n? So if we spend this optimum amount of money on each of those things, what will actually be our maximum output? So we have to remember, even though our answer is 44,000 on labor and 46,000 on materials, the X and the Y are still just 44 and 46. So to find our maximum output, we'll plug in 44 and 46. And you get
5808. 5,808.
5,808. Okay. That looks like a 15. That's not a 15. Oh, and that's not in dollars. Oh my gosh. Okay. Let's back up. Just going to erase this whole thing for a second. So our output is not actually in dollars. Let's go back and look at our problem. The monthly output is N equals this. So output, whatever the situation is, output is going to be how many units we are actually producing based on this budget. So since we don't know what we're producing here, we can just say 5,808 units. So let's go back and look at that graph that we were looking at and see if this all matches up. Hopefully it does. So N we just found is 5,808. And so that does look like, when I put in that value of N, it looks like these two are just barely touching right at a tangent point. And if I click on this, yeah, so it Desmos automatically brings up their intersection point, and it's just 1 point, which means it's definitely a tangent. And 44 and 46 are the X and Y values. So that lambda, adding in that lambda, is giving us a way to figure out just the right place where X, Y, and N come together to give us the biggest output we possibly can have, keeping that budget that we have. Are there any questions about this problem or these problems in general? Okay, so we do have 20 minutes left of class, but this is all of our material for the term. So I don't want to try to like squish in something extra just for my enjoyment. So I would be happy to do another problem like this so we can see it again, or answer any other questions that you have, or just call it a day. So I will open the floor to if there are any requests to do another problem with Lagrange multipliers, or any other general questions that you want to ask.
I'm good.
Did you say that this isn't going to be on the next test?
This is on the final part 2. So it's on the take home test, but not on the test next Thursday. So this is the one you'll be able to like look at your notes and use the steps. And I also put this, like these steps are in the book, but I also put them on this chapter 7 review sheet as well. So you'll notice on the chapter 7 review sheet, there is partial derivatives, and so general optimization. So finding local extreme and saddle points of z of f of xy. So that's what we did on Tuesday, where we're just trying to find the maximum or minimum or a saddle point. And then on the following page, we have Lagrange multipliers to find maximum minima subject to a constraint. So those are just the same steps that we went through. So that's available.
And those are both on the take-home test, right?
Yes.
Okay.
Anything else? Okay, so I am going to hang out until 1:15 unless everyone leaves, and then I will also leave. But if you have questions that you want to stay after and ask, please feel free to do that. I'll be here. Otherwise, have a great weekend, and I'll see you on Tuesday.
Thank you so much, Madeline. Have a great day.
You too. Thank you.
Thank you. Bye-bye.